This video sets out to do two things. First, to work through examples of calculations relating energy, wavelength, and frequency. And second, to learn how the color of light absorbed is related to the color a complex or compound is. There are three equations you should know which relate energy, wavelength, and frequency. E equals h nu, E equals hc over lambda, and C equals lambda nu. Although these equations aren't too complicated, it's important to write down the units as you set up the problems. Frequency has units of inverse seconds, called hertz, and wavelength, lambda, must be in meters in order to cancel. For visible light, we are usually given wavelength in nanometers, so you'll need to know the nanometer to meter conversion factor. Be very careful with the prefix equivalency. It's easy to accidentally write the conversion factor as 1 times 10 to the negative 9 nanometers instead of 1 nanometer. The constants h and c are given, and though we'll use them to 4 digits, 2.998 and 6.626, they are still exact. For the visible spectrum, you should know the order of the colors and how each term is related. At the violet end of the spectrum, the wavelength of light is low and the energy and frequency are both high. Whereas at the red end of the spectrum, the wavelength is high and the energy and frequency are low. One thing we'll see in problems regarding coordination complexes is relating the color of the complex or compound to the color of the light absorbed. The color of light absorbed is not the same as the color of the complex or compound. Whenever we calculate energy, wavelength, or frequency, these parameters and the corresponding colors always refer to the light absorbed. To move between color of light absorbed and the color a complex or compound appears, we use complementary colors. An abbreviated connection that is pretty easy to remember is to line up ROY and GBV like the diagram shows. These connections work in either direction, whether you are starting with the color absorbed and want to predict the color of the complex, or if you're given the color of the complex and want to predict the color of light absorbed. The common mistake with these types of problems is to skip this step and to relate the color of a complex to the relative trend in wavelength, energy, or frequency. So we'll work through a few examples of the calculations, and then we'll move on to a couple problems involving the colors. So in our first example, we are given a wavelength, and we are trying to calculate the energy. So the form of the equation we'll use will be E equals hc over lambda. Because c has units in the numerator and denominator, it's a good idea to make it its own term in the equation, and that way the units, all of the units, will clearly be in numerator or denominator and will cancel more easily. The other thing to remember is that the units of wavelength need to be in meters in this problem. So you can either convert the wavelength beforehand, or you can incorporate the nanometer to meter conversion within this equation. So we have E equals H, which is 6.626 times 10 to the negative 34 joules times seconds. Be careful with that. It's not joules per second. Times C, so I'm going to give that its own numerator and denominator, 2.998 times 10 to the 8 meters over seconds, divided by wavelength. So I'll put that over here, 532 nanometers. And then if I cancel units, I'll have seconds that cancel. And notice that nanometers and meters won't cancel. So including all of the units reminds me that I need to do that nanometer to meter conversion. So I have nanometers in the denominator. That means my nanometers will need to go in the numerator. So I have 1 nanometer equals 1 times 10 to the negative 9 meters. Now, nanometers will cancel, meters will cancel, and we're left with units of joules, which are energy units. As far as sig figs, H is exact. I have 3 sig figs for my wavelength. C is exact, and the prefix conversion is exact. So my final sig figs will be 3 sig figs. So doing the calculation, we have 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8 divided by parentheses 532 times 1 times 10 to the negative 9. And rounded to 3 sig figs, we get 3.73 times 10 to the negative 19 joules. In our next example, we are given an energy and we're asked to calculate the frequency and the wavelength. So it doesn't matter which one we calculate first. I'll go ahead and start with the equation E equals h nu. If I'm solving for nu, for frequency, I can divide both sides by h, and then I can solve for frequency. So nu equals energy, 3.24 times 10 to the negative 19 joules, divided by h, which is 6.626 times 10 to the negative 34 joules times seconds. Joules will cancel, and I will be left with units of inverse seconds. For sig figs, I have 3 in the energy, and h is exact, so my final answer will have 3 sig figs. I have 3.24 times 10 to the negative 19 divided by 6.626 times 10 to the negative 34 gives me 4.89 times 10 to the 14th. The units are inverse seconds, and that is the same thing as hertz. So I can rewrite this as 4.89 times 10 to the 14 hertz. The second part of this is to calculate the wavelength. So I can either use the equation E equals hc over lambda, or I can use lambda nu equals c, because I now have the value for frequency. So if I divide both sides by nu, I get lambda equals c over nu. So lambda equals c, 2.998 times 10 to the 8th meters over seconds, again setting up c with its own conversion factor, divided by frequency. So frequency will be in the denominator, 4.89 times 10 to the 14. Instead of writing hertz, I'm going to include the units in terms of seconds. So the units were seconds to the minus 1, which means seconds will flip to the top. Seconds will cancel, and I'm left with units of meters, but the question asked for lambda in nanometers, so I need my prefix conversion. I have meters in the numerator, so the meters part needs to go in the denominator, so that'll be 1 times 10 to the negative 9 meters, and then 1 nanometer will be in the numerator. Meters will cancel, and I will be left with units of nanometers. For sig figs, C is exact, the frequency has 3 sig figs, and the prefix conversion is exact. So the result will have 3 sig figs. Doing the calculation, 2.998 times 10 to the 8 divided by parentheses 4.89 times 10 to the 14 times 1 times 10 to the negative 9, rounded to 3 sig figs, is 613 nanometers. In this example, we're given two compounds and we're told the color of light that each one absorbs. So I'm actually going to write down the word absorbs so I don't get confused. So compound A absorbs orange and compound B absorbs violet. So the first question is asking us to compare the relative energy and wavelength of the light absorbed. So if we look at the relative order of the colors, remember that the violet end has shorter wavelength and higher energy and frequency. And it's the opposite for the red end of the spectrum, which has longer wavelength, lower energy, and lower frequency. So if we're comparing orange to violet, orange has a higher wavelength compared to violet, and orange has a lower energy compared to violet. The next question is asking for the color of each compound. And for this, we look at the complementary colors, ROY versus GBV. So we can see from that little chart that if the compound absorbs orange, then its color must be blue. And if the compound absorbs violet, then its color must be yellow. In our last example, we're given the colors of two complexes. So I've already written my notes off to the side about how the colors relate. So my complexes A and B have the colors yellow and red. The first question is asking for the color of light absorbed by each complex. So we can see from our complementary colors that the yellow complex will absorb violet and the red complex will absorb green. The next question is asking which complex absorbs light with a longer wavelength. So when we consider the order of the colors, violet light will have a shorter wavelength compared to green light. So to answer the question, the red complex will absorb light of a longer wavelength. And then I guess I should box that part too, because that was the answer to our first question.